Oh, hi there. Just working on my car while I've got some of this time at home. And oh my, what did I do? I got myself oil all over my shirt. How am I going to get that off? It's not going to come out in the wash. I better use chemistry. Remember, I don't want to work harder. I want to work smarter. Now if I put this right in the wash, soap and detergent is going to try to take these out by surrounding these nonpolar molecules with their nonpolar side and bringing it into the water with their polar side. But these grease molecules are big, 12 to 18 carbons long, a little too big for my detergent to really get rid of them. So how can I get rid of these? I have to dissolve them in something that oil and grease wants to dissolve in. And that is another non-polar substance. Just so happens I have WD-40, which is a non-polar light oil, very light oil. So if I can spray my oil and grease stain and saturate it with this WD-40, I can start to dissolve the oil and grease. Blot it off as much as I can with a paper towel. And now that I've broken up these oil and grease molecules with smaller ones, I can use detergent to take this out. Let's give that a try. Okay, I've blotted up what I can, and the smaller WD-40 nonpolar molecules have dissolved or broken apart some of the larger motor oil molecules. I'm going to take this, I'm going to throw it into my washing machine with the rest of my laundry and use just my normal laundry detergent. Pop it in and get to washing. Well, now we've finished our washing and I've put my load in the dryer. Dryer's done, so let's see how that shirt came out. I look around here with my... here we go. Here's our shirt. And looks pretty good. Got that stain out. So what do we see? Polar substances dissolve polar substances. Non-polar substances dissolve non-polar substances. Oil and grease are non-polar substances. They will dissolve in other non-polar substances. Water is a polar substance. It will dissolve things with charged sides, which are polar, and not things that are non-polar. Soaps and detergents have a polar end and a very long non-polar end. So they can try to bridge that gap between the two. Non-polar molecules can't. There is no line that you can draw that can be a positive side and a negative side. So like dissolves like, and you can use that in your everyday life. Polar molecules have a partial positive side and a partial negative side. And we show the partial positive by using that Greek delta, which is a small delta, small d, and it has a positive, a plus sign in the upper right, and the partial negative is the same delta with a minus sign in the upper right. And that just designates a partial positive and a partial negative side. Let's take a look at methane on the left and chloromethane on the right. Methane is CH4, chloromethane CH3 with a chlorine, and you can see the lone pairs drawn around the chlorine. Now the carbon pulls the electrons from the bond a little bit toward it. Each hydrogen is just a proton. So it has a positive charge, a slightly positive charge, or a partial positive charge. And you can see that as I've drawn in the little delta pluses around each hydrogen. And you can see that any way we approach this molecule, it's always the same. Any molecule coming at it will hit a partial positive charge. Now let's take a look at the chloromethane. The chloromethane has hydrogens around the left side, but the chlorine itself has lone pairs. Those lone pairs have negative charges of their own, giving the chloromethane a partial negative charge around the chlorine and a partial positive charge around the hydrogens. Now, if we look at this, we can actually draw a line to separate the negative part of the molecule from the positive part. This side of the molecule is going to be somewhat negative, and this side of the molecule is going to be somewhat positive. Kind of like a magnet. That's why we call chloromethane a polar molecule. While methane, well, we can't draw a line in any way that's going to separate positive side from a negative side. So methane is nonpolar. Let's take a look at water. Water is a bent molecule, and those two lone pairs on the oxygen give it its bent shape. Those two lone pairs are also areas of negative charge, giving that side of the water molecule a partial negative charge. The hydrogens, on the other hand, just protons with their single electron involved in the bond, give this a partial positive charge. Can we draw a line through the middle? Well, we can. And if we can draw a line through the middle, leaving a positive side of a molecule and the negative side of a molecule, then the molecule must be polar. And if the molecule is polar, things that are charged, like sodium and chlorine and sodium chloride, or calcium and sulfate and calcium sulfate, will dissolve in it. Things that are nonpolar will not, because the polar molecules kind of are like little magnets and they want to stick together. As they stick together, they'll squeeze out something that's not polar, something that doesn't have a negative side and a positive side. And when it squeezes those out, you have a separation between oil and water, a separation between polar and nonpolar molecules. So we have polar molecules and we have nonpolar molecules. Polar molecules are the ones that act like little magnets. They have a positive side and a negative side. They attract each other. They pull together. And that's going to give them certain properties. Properties like a very high boiling point. So they don't want to come apart. It's going to take more energy to break them apart. Nonpolar molecules, gases like methane, carbon dioxide, which are about the same size as water, don't have those hydrogen bonds pulling together like small magnets. So at room temperature, they're gases. It takes a much bigger molecule, like oil, to stay in the liquid state. Polar molecules also have high boiling points, high melting points. They like to stick together. If we took a penny and we dropped water droplets onto the penny, they would beat up before they fell off. If we took something like hexane, which I'd love to do in the lab, but we're home, and I doubt that people have hexane lying around the house. But if we drop that on a penny, about 4, 5, maybe 6 drops, and it would fall off the edge. There's no cohesive force strong enough to pull it together. So what I'd like us to do is start off with a worksheet that I've put on Google Classrooms and see if we can kind of go through it together, putting together what we know about polar and nonpolar molecules. Okay, here's the polar effects worksheet. I felt this would be the best way to do it, is just to do this together. Name, your name goes up here, the date, and what class you're in. Don't forget that. Now, you're going to draw first structural formulas of N2Br4, which is dinitrogen tetrabromide. You remember the names? And this CH3Br is methylbromine. CH3 is called a methyl group. So it's methylbromine. And determine if they are polar or nonpolar. first create structural formulas for these molecules. Puts the Lewis dots in. Put Lewis dots in to show where the lone pairs are. And then mark the areas of partial positive and partial negative charge with the delta pluses, delta minuses. So start with nitrogen. It's going to be bonded to another nitrogen. There are 4 bromines, Br, 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 Br. There's a lone pair on the nitrogens, and the bromines each have 3 lone pairs. Let's put them in. Now let's take a look. Is there going to be an area of negative charge here? Absolutely. Let's put that delta minus. One here, delta minus. One here, yes, and one here too. Is there any area of delta plus? Can we draw a line that can cut in some way that one part is negative and one part is positive? No, I don't think so. It's negative on all sides. Therefore, this thing is a nonpolar molecule. Let's try the next one. Methylbromine. C, Br, hydrogen, hydrogen, hydrogen. The bromine has lone pairs, giving it a delta minus charge. The hydrogens, well, they're just a proton. There are electrons involved in the bond, so this is more of a partial positive area. On this side we've got partial positive, on this side we've got partial negative. We can draw a line right down the middle, well, not down the middle, but on one side of having positive and one side having negative. This is therefore a polar molecule. So we have polar, we have nonpolar. Some things we want to learn about polar and nonpolar molecules are here on this table. Think of polar molecules as teeny tiny magnets. Magnets stick together. Nonpolar doesn't have that magnetic pull holding them together. So when we say which one would evaporate quickly, it would be the one that has less pull on it. So nonpolar would tend to evaporate quickly. What about beating up on surfaces? Now, a polar molecule like water will tend to form a little bubble if we put it on, let's say, a penny. Whereas something like methylbromine would just tend to fall right off. So, beat up on surfaces, that would be a polar molecule. What do you think for these other ones? Put check marks in the columns where you think they go. This next activity talks about water. Draw the structure of water. Okay? H, O, H, with 2 lone pairs. This is going to be a slightly negative side. This a partial positive side. We can draw the line through the middle, so it's polar. Isopropyl alcohol is going to have a carbon and OH, CH, H. That oxygen has lone pairs. Look for the lone pairs. Where you see lone pairs, that's a partial negative. Look for hydrogens. Where you see hydrogens, partial positive. We can put a line like that, can't we? There's a negative. This is positive. It's not through the middle. It's not through the middle at all. But there is a slightly negative side and a slightly positive side. So isopropyl alcohol will be somewhat polar. Not as polar as water, but it will dissolve in water. And it will also dissolve things like pine sap. So if you get pine sap on your hands, you know, from climbing a pine tree or working with pine wood or people park their car under a pine tree, get pine sap on their car, a little alcohol will dissolve that right away. Acetic acid, CH3, CO, double bond O, single bond O, H. Let's get those lone pairs in there. Delta negative, delta negative. What's going on the other side? All hydrogens. Where you see hydrogens? Positive. Can you draw a line separating out negative and positive? You can. Write down what you think that's going to be. Hexane? What's that going to look like? Polar or nonpolar? Ethyl alcohol? And kerosene? Well, there's 9 carbons. And I'll leave that one up to you. When you finish these, try the rest of the sheet. I've drawn in the molecules for you. All you need to do is put in lone pairs, figure out if you've got a negative side, a positive side, and then determine if they are polar or nonpolar.